Okie dokie. Next, we're going to keep talking about vector stuff, but this time we're moving into the calculus of vector valued functions. So the last video was about vector valued functions specifically. Now we're going to take that the next step further. So the first thing we're going to want to talk about is if I have a vector valued function, r of t, let's just say that this is just a very generic vector valued function where I just have f of t and g of t, right? Well, what happens if I want to take the derivative of that function with respect to time? The way this is going to work out is actually just going to be pretty straightforward. You just take the derivative of each component. Nothing too crazy here. Okay, so that one works out pretty straightforward. This is pretty much what we're expecting to happen. And now let's look at, well, what if I want to take the derivative of some vector valued function times just some function of t? Well, I think your intuition here might lead you the correct way to say, well, that just looks like a product rule to me. And you know what? You're totally right. So in this case, we could take f prime of t and then multiply that across. I'm going to use different notation here. So we'll multiply that across r of t. Now, keep in mind, this f of t is not a vector, so this is not a cross product or a dot product. This is scalar multiplication of a vector. So f prime multiplied into r of t, and then plus just regular f of t multiplied into r prime of t, right? Works out just like we think. Okay, so the next one we've got is going to be the derivative of the dot product of two vector valued functions, right? And you know what? This one works exactly like we think it's going to work too. We're just going to get r prime of t times u. Ooh, that's terrible. There we go. U of t. And then we're going to say plus, and then we have r of t and u prime of t. Now, the only catch is these are actually dot products because these are vectors and you can't multiply vectors. We talked about that last time. Okay, we're just going to talk about one more and then we're going to do some examples. Okay, so we got a vector value function r of t, and then we're going to cross product that with a vector valued function u of t. And I think you know exactly what's going to happen here. We are in fact going to get r prime of t cross u of t plus r of t cross u of t. And then there's just one little more we should talk about really quick just in case. So we've got the derivative of r of t dot u of t again, so two vector valued functions equaling a constant. Now remember, we're going to also take, I'll write this over here, I'll write ddt of the constant. Okay, so this means that we're going to have our just normal dot product rule here, right? So we've got this guy here. So I'm just going to copy and pull down so I don't have to rewrite it again. And then that is all going to equal, well, the derivative of c is just 0. So that equals 0 now. Okay, so those are all the important formulas from the textbook. And so now I'm just going to come over here and grab my examples and we'll work on those. So we're going to pull these guys and get a little sneak peek at some of the other examples I want to work on today. So we're just going to take these guys, put them right here, and then we'll work them out to the side over here. I'm going to start A with this blue color. So we're taking the derivative of r of t that I've underlined with this blue color. Okay, so this one's pretty straightforward. We've got just one vector valued function here. So we don't need any of these product rules or stuff yet. We're just going to take the derivative of the components separately, and that's pretty much all we're going to do here. So within our brackets, we'll take our derivative of this entire x component, so everything connected to the y. So derivative here is going to distribute across the addition. So we've got 6t plus 8, take the derivative. The 6 is going to be multiplied by just the derivative of t, which is just 1. And then we have the derivative of a constant, which we already know is 0. So this whole piece of our x component is just going to go down to 6. Okay, so we got 6 for our x component. And now for our y component, or our j component, whichever way you'd like to say it, we have kind of the same idea. We're just going to distribute our derivative across all of this. I really hope if you're in Calculus 3, you know how to do your derivatives pretty well. So it's just applying it to a new concept. So now we have t squared, so it's going to be 2 times 4 times t, which is 8t. Okay, and then we have our plus. Derivative of 2t is just 2. And then we have this guy here. When you take the derivative of a constant, you're just going to get 0. Come on, little tablet, you can do it. There we go. Okay, so since we got plus 0, we're done with that. That is the r prime for the one underlined in blue. Okay, so let's do this next one here. B, we're going to underline that with green. We're going to take the derivative with respect to time of that r of t, and that is going to equal for us derivative of 3 times cosine of t. 3 is constant, so that just comes out of our derivative. We're just going to take the derivative of cosine, which is negative sine, so we should get negative 3 sine of t. And now on this other side, we have 4 sine t. Derivative of sine is positive cosine, sorry. So we're going to get 4 cosine of t. And that equals our r prime for the function highlighted in green. Let me make sure to use my vector notation on this side too so we don't get confused. These are still vectors. Okay, let's do this third one now, and we're going to underline it in white. So now we have the derivative with respect to time of the vector valued function that we have here. So this is a 3-component vector, and I realize I missed writing the k hat here. I apologize. Okay, so let's take our derivatives for each component. So this one with 3 components starting, so we'll get 3 components coming out. Now et sine t, that's a product rule inside, right? So this may come back later where we have to do maybe a more complicated like dot product of vector value functions, and then within them we might have a product rule inside as well. So even though we're taking the derivative of the vector valued function and we care about the r prime of t, we still have to follow all of our rules inside. So since these are both with respect to t, we do have to do a product rule here. So we'll get e to the t, which is the derivative of e to the t times sine of t. And then you'll say plus e to the t times the derivative of sine of t is just cosine of t. And all of that is our x component. Okay? All right, so our next piece here is going to be et cosine of t. So the derivative there is e to the t, which is the derivative of e to the t times cosine of t. Now the derivative of cosine of t, again, is negative sine of t. So we've got minus instead of plus because of that. And then you have et sine of t. Okay, and that's our y component. And now all we have left is this negative e to the 2t. So the negative is going to stay. And then e to the 2t, the derivative of that is just going to be 2 times e to the 2t. Okay? And that comes from your chain rule, actually. And then there we go. We're done. So that's just derivatives of a vector valued function, which is, I think, a whole section on its own. But we're just going to move straight into this next piece where we're going to use some of those properties we just wrote down, and we're going to do some stuff. So I'm going to move those over for us so we can see them a little easier. And then I'm not going to scroll back up to the properties because we're just going to work through these anyways. So we don't need to go back to the properties, and they all come from stuff we're kind of expecting anyways, so we should be okay. So we're given this function, this vector valued function r of t, and then we're given another vector valued function u of t. They equal these things here. We have both 3-dimensional vector valued functions with respect to t. So this one's going to get a little tricky pretty quick. So we're going to start by taking the derivative of the dot product of both of these. So what we remember is that the derivative of the dot product is equal to the product rule. So we know we need to do r prime of t dot u of t plus r of t dot u prime of t. Right? We know we need to do that because we have the dot product and the derivatives. We need the product rule, and then we can do the dot product part. Now we're not going to do the general form of this where you have to write just a whole butt ton of like components and stuff, because that's just not very fun. We're just going to do it with these functions we were already given here, this r prime of, or this r of t and this u of t. So you have two options here. If you're going to do a bunch of these with a few versions of your r prime or your u prime, it is worth it to just separately write down your u prime and your r prime somewhere and then plug them in as you need them. In this case, we're only going to use the r prime once, so I don't think it's really worth the time to do that, but it can be a good strategy, especially if you have multiple problems using the same vector valued functions. So in our case, what we're going to do is we're going to take the derivative of r as a vector, and then just so we can keep track of things, I'm actually going to write these as column matrices. It's the same thing as vectors. So we're going to take the derivative of our r of t function here. So we're going to get 6 for our x component, and then we have 8t plus 2, and then we have just 5 for our or z component, sorry. And then we're going to dot product that with just u as it is. So we get t squared minus 3, and then we get 2t plus 4, and then we get t cubed minus 3t. Okay, so that is r prime of t dot u of t. And then we're going to add r of t, and then the dot product of r of t and u of t is the better way to say that. So 6t plus 8, nothing changes. 4t squared plus 2t minus 3, and then we have 5t down here. Okay, and then we're going to dot that with the derivative of u prime. And I've already written u prime over here, so we can actually scroll over. So we have this x component is going to be 2t, because the 3 is going to go away. Then here for the y component, we're just going to get 2. And then for our z component, we'll get 3t squared minus 3. Okay, now we get to take our dot product, right? In this form, it actually does make it a little more straightforward to do our dots. So what we're going to have is 6 times t squared minus 3 plus 8t plus 2 times 2t plus 4 plus 5 times t cubed minus 3t. And then the plus in the middle stays the same, and we'll do our other dot product now. So we get 6t plus 8 times 2t plus 4t squared plus 2t minus 3 times 2 plus 5t times 3t squared minus 3. Okay, now we just got to distribute all of that and simplify. So we'll get 6t squared minus 18 plus 8t. Oh, wait, hold on. Not 8t. That's a FOIL. So we get 16t squared, and then 8, 16, 24, 32t plus 4t plus 8 plus 5t cubed minus 15t plus 12t squared plus 16t plus, we got 8t squared plus 4t minus 6, and then plus 15t cubed minus 15t. Oofa. Okay, now we get to go through and combine it all. So we'll start with our highest term. So we get 5t cubed and 15t cubed. So we got 20t cubed, right? Both positive. Okay, so now we do 6t squared plus 16, so that's 22t squared. So cross those out so I know we did them. 22 plus 12 is 34, plus 8 is 42. So we get plus 42 t squared, 32t and 4t, that's 36. Now, this one has some subtraction in it too, so I'm not going to try and do that in my head. So we got 36 minus 15t plus 16t, so we can actually just rewrite this as plus 1t. So plus 1t. Okay, so that takes care of that and that. And then we got 4 and negative 15, so it's minus 11t. Okay, and then negative 18 and 8 is negative 10. Minus 6 is negative 16. That one wasn't too bad. Okay, so just one last simplification since I did take an extra step. Okay, and then 36 plus 1 is 37, minus 11 is going to be 26t minus 16. So this is what the derivative of the dot product of r and u are, where r and u are vector valued functions. Okay. Next we're going to do the cross product of u and u prime. So before we dive into what that is numerically, let's think about this for a second. So we know that that's going to be u prime of t cross u prime of t, and then we're going to add that to u of t cross u double prime of t, right? Because that's our product rule. Now, we have the same vector crossed with the same vector, and we already know that the cross product is supposed to tell us a orthogonal vector, and it uses the sign property. So if we have two of the exact same thing and we take sine of that, that's sine of 0. Sine of 0 we already know is 0, so this first part actually just completely cancels. So we don't even have to worry about that. So now we just have to do the cross of u and u double prime. Okay, so we're going to take u of t, we're going to cross that with u double prime of t. Okay, now we already have u written down, so we're just going to rewrite that. So we got t squared minus 3, and then 2t plus 4, and t cubed minus 3t. Now we need a second derivative, so what I'm actually going to do is I'm just going to use some space over here on the right and say, okay, well, u prime of t we already know is 2t, 2, and then 3t squared minus 3. So now I just need to take a derivative of that. So I'll get u double prime of t is equal to, now derivative of 2t is just 2, derivative of 2 itself is just 0, and the derivative of 3t squared minus 3 just becomes 6t. Okay, so now I have the thing that we're going to do the cross of over here. So we're going to do cross 2, 0, and then 6t. Okay, now again, you can use the formula to do the cross product, or you can just do the determinant. I personally prefer doing the determinant. I just think it's easier than trying to remember a formula. We'll see if that's enough space for this. So we're going to take this first vector that we have. That's our first column. So we've got t squared minus 3, 2t plus 4. Yeah, it wasn't enough space. Okay, and then we have t cubed minus 3t. Okay, and then our other vector is our other row. So we get 2, 0, and 6t. Okay, so we're going to take the determinant here. So we're going to start with our I hat. We've got a 0 here, so we're just worried about this 2t plus 4 times 6t. Okay, so that's for our I hat. I'll use the I hat notation for now. Okay, so then we have our j hat. So this one we are actually going to have everything, and then we'll remember our coefficients and how they switch signs. So we've got t squared minus 3 times 6t minus t cubed minus 3t times 2, and that's j hat. And then finally we have our k hat, We know this one's going to be 0, so we've just got the negative, I'm actually just going to write negative 2 times 2t plus 4. Okay, and that's k hat. Okay, just a little bit of simplification and we'll be there. So, come on tablet, do your thing. There we go. So we've got 12t squared here plus 24t I hat, remember these are vectors, minus, now we've got 6t cubed minus 18t on the inside, and that is also subtracted by, I'm going to actually add one more set of parentheses just in case anyone gets confused how this part's about to work. Okay. Okay, so now we have minus t cubed times 2, so that's 2t cubed minus 6t. Okay, still keep track of your parentheses, be careful. Easy to make little mistakes here. So now we get plus, and then we have negative 4t, and then minus 8k hat. Okay. This first piece doesn't really simplify at all, so we can just leave it exactly how it is. So plus 24t, and then I hat. Now this next piece, 6t cubed minus 2t cubed, that's 4t cubed. And notice I didn't put a sign in front yet, so we'll see what we want. Now we have negative 18 minus negative 6, that's plus 6, so we get 12, so negative 12t here. And then let's just go ahead and distribute that negative through, just so we don't have to worry about losing it by accident. Okay? And now all we have down here at the end is just our negative 4t minus 8k hat, right? And then this is plus in front. Okay, so all of that is what the derivative of u, the vector valued function u, crossed with the vector valued function's derivative of the same function was. Okay, I think that's all I wanted to do for, derivation. Okay.